If you are ready, you may.
Okay, so I can just start whenever. Looks like
Yeah.
yes. Okay. Well, good afternoon. My name is Tyler Summerlin, and for my GIST 909 final presentation, I will be looking at measuring ground deformation using interferometry. So what is interferometry? It is part of the remote sensing field, and it is active remote sensing. So it uses its own source of emission to emit, reflect off an object, and measure the return, as opposed to passive remote sensing, which would use an alternate source of emission, such as the sun, to reflect off of something. And interferometry is sourced from SAR, which stands for synthetic aperture radar. And these are almost always spaceborne satellites. And with radar, it sends out microwave radiation, and the resolution is dependent on the wavelength of the sensor and the length of the antenna. So with a satellite, it's not very feasible to send up a massive radar antenna. So instead what they do is they synthetically increase the resolution by taking multiple exposures of a shorter antenna to represent a longer antenna. So that's how it's synthetically increased. And interferometry is a comparison between two SAR collections. So this image here on the right shows a satellite being passed over the same object twice, and a comparison is made between the data that it collects. So for this project, I used the Sentinel-1 satellite, which is operated by the European Space Agency. And as you can see, they have multiple different acquisition modes. But regardless, it almost always flies at around 700 kilometers above the surface. And for this presentation, or this project, I used the interferometric wide swath mode, which also stands for IW. And that's 3 subswaths. So for every data set, there are 3 strips of data. And in each of those subswaths, there's between 6 and 10 bursts, which are basically split up swaths that are overlapping. So with interferometry, there are 3 main values of importance. There's cohesion, phase, and amplitude. So cohesion is a comparison between one SAR data set and the next on how similar they are. So towards the center of this image in this white area, you can see it's mainly just like rock. It's the big island of Hawaii, so it's a lot of volcanic plains. It's stuff that over 12 days, which 12 days is the repeat cycle of Sentinel-1. Over 12 days, you don't really expect rock to change very much. But then towards the coast, we have the lower cohesion values of forest. So over 12 days, you'd expect forest to change quite a bit. And then we have phase. So phase is the actual data that we're looking at for interferometry. So it is the round trip time of the microwave signal measured in wavelengths. So towards the middle of the island, where we have this large volcano, we have a lower phase value, which is indicative of a higher elevation. And towards the top left area, we have a higher phase value for lower elevation. On the right, we have the actual raw data value, which is amplitude. And amplitude is just the strength of the return, and it doesn't really give us a lot of information for interferometry. But it is interesting, you can actually see the individual bursts in it where it's segmented, and you can see part of the subswath overlap on the right side. So our area of focus is Big Island, Hawaii, if you haven't noticed so far. And in particular, we're looking at the East Rift Zone, which is towards the eastern side of the island. And a rift zone is an area of rifting or splitting rock associated with earthquakes and volcanic activity. And in particular, we're looking at an area in 2018 where there's a 6.5 magnitude earthquake off of the coast about a mile to the east. And we will see how that earthquake affected the rift zone. So to do that, we have this long list of processes that we're going to go through. So this is all done in a software called SNAP, which stands for the Sentinel Application Platform. It is provided free by the European Space Agency. and its primary use is in interferometric processing. So as I mentioned earlier, each product has 3 subswaths. One of them is entirely over the ocean, so we will just ignore that one. But the other 2 subswaths we will input as the input read objects, and we'll do quite a bit of processing on them separately before merging them and continuing with processing. So all of this processing can be split into 3 general categories. There's pre-processing, which splits the subswaths, applies a few different files for corrections, and will co-register it, which I will get into co-registration on the next slide. Then there's interferogram formation, which will take those co-registered products, remove the bursting, and then create the interferogram and filter it. And then finally, we have the phase unwrapping, which will take that interferogram, unwrap it, and correct for or calculate deformation. So for the pre-processing, on the left, we have the raw input dataset. So this is actually one individual subswath, and you can see the bursts going left to right. And you can also see on the coast, there's these jagged edges. Those are actually the overlaps between the bursts. So each burst is 1 and about 1/5 of the next burst. So on the right, we have the co-registered product. So co-registration takes the 2 input data sets and tries to overlap them. And it might be difficult to tell in the presentation, but there's yellow and blue pixels, and they're overlaid perfectly. There's no overlap in the ocean, so we have proper co-registration. With that co-registered product, we can find the phase values. So on the left, we have the raw phase. And as I mentioned earlier, there's a big volcano in the middle of the island, and we see these color bands. Those are called phase fringes, and you can think of them as contours. Every phase fringe cycle indicates a change in elevation, but it doesn't indicate which direction the elevation is going, if it goes up or down. So also on the outside, we have all of this static noise, which indicates the low cohesion from the forest. So we go through a few processes in between this, but we eventually remove the topographic phase. So it's basically how it sounds. So we take the phase from the topography. So all of the phase that's being added up from the volcano, for instance, is removed, and we now have a generally flat surface. But you can see there's a few phase cycles going through. So across the entire island, it may have moved about 1 phase cycle, which doesn't mean a ton. But on the left side, you can see there's some pretty dense phase fringes. And the left side is actually the east side of the island. It's flipped and deformed from the tilt in the aspect of the sensor. So with that interferogram, we will unwrap it. And phase unwrapping is done through an application called Snafu. It's a networking flow algorithm. And what it does is it splits an image into a specified row and column count with a specified overlap. And for each of those tiles, it will try to find all of the phase fringes and accumulate them. So for this was the hardest step of the entire project. It took me about 2 weeks to get a artifact-free output that made sense. And I did that with the DEFO method, which stands for deformation. So as I mentioned, it tries to accumulate the phase. So on the left, we have all of these phase fringes. And on the right, with the unwrapped phase, all those fringes are added up and accumulated. And in the coast and out in the water, there's quite a few artifacts, but those get removed in a later step. So to quantify the phase, so going across the east rift zone with the wrapped phase, it will go up and down with the phase cycle. So it goes from -2.5 to 3 phase towards the peak, and then it'll go back down. And then with the unwrapped phase, with that exact same profile across the east rift zone, we will go all the way up in phase up to about 85 and back down. So here's the actual area that I took the profile plot of. So it goes right across the east rift zone. And one of the most important steps in the whole process is to find the actual displacement, because up until now, everything has been measured in phase, which is hard to think about quantitatively, like how far is phase. So this converts it to meters with this function here. So it takes the negative of the wavelength over 4 times pi multiplied by the change in phase. So we go from a rising phase value to a lowering displacement value, which makes sense because as the phase increases, the displacement should move away from the sensor. And it's a little hard to tell on this, but we'll see it more closely later. But it goes down to about negative 0.4 meters. So here we have the actual final output. So this is the line of sight displacement map. So this is actually the shape of the east rift zone, which is interesting. So along the very center of it, it sunk about 40 centimeters. And then there are a few other localized areas of sinking. And then towards the coast, it actually rose about 20 centimeters. And one interesting thing is the right side and a little bit on the top left, you can see some artifacts. And this is all from the low cohesion from the forest. So even though I did quite a lot of work to remove and minimize the impact of the cohesion, it still played a pretty major part. And one important thing to note is this is line of sight displacement, which basically means from the sensor, which the sensor in this case was about 25 degrees off nadir or off directly perpendicular to the surface. It moved away from the sensor 40 centimeters. So it didn't necessarily move down into the earth 40 centimeters. So that means it could have moved down 40 centimeters or down slope 40 centimeters or a combination of. So to go into what actually caused the sinking. So as I mentioned, the rift zone is an area of splitting rock. And what likely happened was intrusion, which is just a subsurface eruption. And when you think of Hawaii, you think of lava flows and lava plains, and that's exactly what happened after these earthquakes. There were quite a few lava flows. And what likely happened was a graben, which is essentially a rift valley. So when you have two parallel faults and it's extended, so with the earthquake offshore, it likely pulled these rifts apart. It causes the area between the faults to sink. So that's likely what happened here. So with the entire project finished, there are a few things I would have changed if I was to do this project again. One thing is to collect or to use both ascending and descending collections. As I mentioned, I could only calculate the line of sight displacement because both of my collections were over almost the exact same point in space. And you can think of this like triangulation. If you have two perspectives, you can find the exact distance and location of an object. Because I only had one perspective, both of my collections were from the same place, I couldn't find the horizontal and vertical components of that displacement. Additionally, I would try to find an area with some lower vegetation impact. It played a pretty major part of the entire process. A lot of the work went into lowering the effect of the low cohesion, because even in the very beginning, the entire East Rift Zone, at least the eastern portion, was completely covered in vegetation. But ultimately, some of the data still slipped through, which is good, but having lower vegetation impact would have helped. And finally, using some other sensors. So Sentinel-1 uses C-band microwave radiation, which doesn't penetrate foliage very well. There are other satellites such as the ALOS-2, which is operated by Japan, and it uses L-band, which can penetrate foliage and would have prevented a lot of the issues with low cohesion. And with that, that is the end of my presentation. So thanks everyone for listening. If anyone has any questions, that would be a good time.